My name's Chuck Calio with IBM. I'm the offering manager for Neo4j on IBM Power Systems hardware. And I'm going to take you through an interesting journey that we have with Neo4j around actually what we call the recursive properties of Neo4j and IBM Power Systems. So we actually use Neo4j to design our servers, and we optimize Neo4j on our servers. So talk about that. So piece of important information up there is probably my email. So don't hesitate to call or give me an email. If you need anything from us, we're more than happy to work with you. So we're going to do a co-presentation. I'm going to go for 20 minutes. Then my colleague Kiram here is going to talk about using Neo4j to design IBM hardware. So you've heard a lot of case studies about fraud detection and recommendation engines. We're going to actually talk about a little something different here. Mix it up a little bit. So IBM, in the unit I'm in, we make server hardware and accelerators for Neo4j. So the server hardware runs Neo4j, primarily the graph database, and the accelerators extend the memory and accelerate the graph algorithms. Now at this conference, you're going to be hearing more about graph algorithms, so it's important to cover that topic now as well. So we have really 300 worldwide companies contributing to the design of our servers. And as you can imagine, there's a lot of different combinations and permutations of that. But primarily two main points I want to make in terms of what's new or what's happening in hardware. This particular set of products is optimized for Linux. So unlike an Intel that has to optimize for both Windows environments and Linux environments, we just focus on optimizing for Linux. And the second thing is, the biggest thing happening in hardware now is around acceleration technology. And so those are in really two domains. You've heard about GPU accelerators, and those come from NVIDIA, and that's primarily in the AI domain. And then FPGA accelerators. We partner with Xilinx and Nalotech, and we'll talk through some interesting examples of the usage of that with Neo4j, both databases and algorithms and acceleration of that. So we're totally open. We have over 100,000 open source packages on there, and we have a deep optimization of Neo4j. We actually use this hardware to optimize Neo4j software, and we use their software to optimize our hardware. It's a pretty interesting mix, and I'll talk a little bit about the interesting recursive nature of that. So we do have a complete modern data platform on our servers that I just spoke about that were designed with Neo4j. We do offer a number of open source relational products, so we do acknowledge that the relational model is still very much alive and well, in particular for the transactional environments that are very popular down here in financial services sector, and people who have SQL skills, so we maintain that. An interesting thing I want to point out here, in addition to the traditional commercial relational products that you're used to, the DB2s, the Oracles, and such, we offer some interesting variants of or open source databases that are relational that run on Linux on Power. So for example, EDB from Postgres is pretty popular in that space. Open source, much lower cost, but you get the transactional properties of a relational database, and you also get to preserve the SQL knowledge that you and your programmers have, and that sort of relational view of the world and the transactional goodies that you get from that. Now, in the middle is the interesting environment that me and a couple of my colleagues are focused on, the NoSQL space. So we really have 4 different offerings in this space. We have a close partnership with MongoDB around the document space. We also focus with Redis around the key value store, the data structure store space. We do some work with Cassandra, and then we do a lot of work with Neo4j, and I'm the offering manager for that product. So we span document, key value store, columnar wide, and graph. We have a few others in there. We also have a very close partnership with Hortonworks around Hadoop. The one thing I want to point out on this chart is what we're starting to see is more and more adjacent solutions. So people who have a Hadoop data lake and are interested in Neo4j, people who have Spark and are interested in Neo4j, people who have Spark and are interested in Cassandra, people who have Spark and want to cache ML modules with Redis, using Redis with MongoDB. So we start to see this adjacency in the database space. The second thing we start to see is most database vendors now are also becoming application providers. So the pure play database is sort of leaving us a little bit now. So you see, for example, Neo4j branching into search algorithms, Redis offering Redis modules, MongoDB offering a lot of mobile application platforms, and then so on and so on across that space. For example, Hortonworks is 29 different products now in a bundle. The third tier of our approach is DevOps. So we do have partnerships that work with Pivotal Cloud Foundry and also Bluemix. So really our view is relational, NoSQL, and DevOps. And I'll talk about on-prem and cloud delivery, and then the newest thing happening in hardware is acceleration technology for the really tough to solve algorithm problems. I'll talk a little bit about that. Basically, I used to give this presentation and say I'm really about one thing, helping you make better decisions. But now I've changed my sort of song here. I actually help you and machines now with AI make better decisions. And then the third thing is, I get a lot of recently, is I help you and AI algorithms make faster decisions. So really I've seen this evolve from my time working in databases where my value proposition is I help you make better decisions, but I also now help AI algorithms make better and more accurate decisions. And now the big thing now is all about speed. So those use cases that need to go extremely quickly are really a focus area for that. So here's the magic underneath that. So at the end of the day, databases need a lot of CPU to I/O bandwidth. This is the single defining factor right in the middle there, 4x memory bandwidth that gives us the incremental differentiation. On the left is oftentimes with a database, you do need multi-threaded workloads, in particular in the load process, or if you're going to also run a lot of different apps on the databases. Databases themselves don't burn a lot of CPU, but typically the surrounding products do, and the often overlooked thing in a sizing of a database environment is load, and that's where you can also benefit from a lot of threads per core. Caching, if you improve caching by 1%, your instruction efficiency goes up through the roof, and we are open. The other thing I want to talk about a little bit more on the bottom there is our focus on both databases, modern and traditional, and analytics at the same time. So we kind of view those two as the same thing, databases and analytics. Why would you want a modern database? Well, you're probably going to be doing analytics and AI. And why would you be doing analytics and AI? And how does that relate to databases? Speed and accuracy. So we have an executive relationship with Neo4j. We have constant interlocks. I've managed a lot of software vendor relationships in IBM. This is a great company to work with. Neo4j is a great company to work with. Super, super good company for you to become involved with going forward. I've had a lot of ups and downs, and it doesn't always go well with vendors. This relationship between IBM and Neo4j is absolutely terrific, and it spans multiple parts of IBM. We're doing work with them in systems. The Watson team has done work with Neo4j to look at using Neo4j and Watson applications for travel and those kinds of things. We're doing some work with the IBM software unit, and then we're doing some work with the IBM security unit, and other parts of IBM are expanding it. And you'll hear from my colleague, Kieran, in a few minutes on how we actually use Neo4j to design our hardware, which is, I think, a pretty cool use case. So we're in luck, Kieran. I think they forgot they screwed the clock up, so we have a little bit more time now. So I'll take you through a little bit of a journey between IBM and Neo4j. And as I sort of stepped back and looked at it, the word that came up is recursive and how we keep calling each other. So it's interesting. So 3 years ago, we just basically ported Neo4j Graph to run on IBM Power 8 hardware, just a straight out port. And when you do that, you get some advantages from the hardware, but we didn't get a lot from that. The second thing is then we introduced this new accelerator called CAPI. So it's our coherent accelerator processor interface that basically in the first rev extended the memory footprint that you could have on an individual server to run larger Neo4j graphs in memory. So that's the second thing we did. So we started out running Neo4j on IBM Power 8, and then we used Power 8 CAPI to optimize Neo4j performance. The third thing is then we did some benchmarks for some customers that generated some traces that actually optimized Neo4j software. So we started out running Neo4j on our hardware. We learned from that. We changed our hardware to get better with Neo4j. Then we ran Neo4j on our changed hardware, and we made Neo4j better. The next thing we did after that was a lot of our AI customers that run a slightly different product that's optimized to contain NVIDIA GPUs and Power 8 CPUs at the same time started also asking to run Neo4j on that. So Graph plus AI. And to do that, you really have to have both types of accelerators, FPGAs and GPUs. So we really changed our hardware to accommodate the newer Neo4j AI environments. Then again, we use Neo4j, the product, to design the next generation of our hardware chips. You probably heard a lot of use cases about fraud detection, master data management, identity management, supply chain optimization. But my colleague will be the first to present using Neo4j to design hardware. So it's a pretty interesting presentation, and I'm going to get out of his way really quickly here. After that, we then took some more traces of Neo4j on Power 8, and we used that to design our new CAPI in Power 9, including newer programming languages. And then finally, we're at sort of two greenfield areas. One is Neo's coming out with graph algorithms. So I think this is really going to be a super high growth area for the industry. So we're right hand in hand with Neo on that, and we'd like to be able to optimize the graph algorithms. We've sort of done the work on the database and the graph apps, so now we're branching into graph algorithms, things that determine centrality and other things, search and all those kinds of graph algorithms, and to optimize that with our acceleration technology to work with Neo4j on that. And then one of the biggest things in the future, I think, is going to be the intersection of Neo4j graph and AI, specifically machine learning and deep learning. And in that scenario, you have available to you for algorithm acceleration, multiple type of technologies, both FPGA and GPU. So it's a really interesting and fascinating journey. The common theme is that we keep calling each other and using each other to solve our problems. And it's really interesting. Neo4j has very high value to us in that configuration. So I'll just talk briefly about this. I want to give this over to Karen. So we do have both a protocol, and it manifests itself in the face of a card that can plug into our processors that basically contains an FPGA, and that FPGA is from Xilinx, extra memory that we can prefetch and put Neo4j data into, and then two NVMe sticks that we can use to extend our memory capacity from anywhere from 2 to 8 additional terabytes per server. Can actually go larger than that because one variant of the card has a cable connector in it that you can hook up to a flash array that can have up to 56 terabytes of NVMe in it. So in essence, it's an NVMe over fabric access that can allow you to have one graph that's 56 terabytes. We don't have a lot of customers that need that right now today, but the biggest theme I hear is customers start to use Neo4j and then they say, wow, this graph got really big really quickly. So we are a good solution to look at if you have graphs larger than a couple hundred gig. I know that's not everybody, but if you do, you can look at us and this CAPI technology. It manifests itself in the first release as really 1.8 better performance per an Intel server. These numbers get a lot better really quickly when you look at graph algorithm acceleration. So this is like the most conservative case is 1.5 to 2x better than Intel. So if you want to reduce the cost of your hardware or have the ability to run more Neo4j on your same hardware, this would benefit you in both cases. The other thing I want to point out on this chart is an IBM Power 8 S822LC Big Data Analytics 20-core server is less than 20,000 bucks. So we're not talking about $1 million investment here. We're talking about a server with a list price of $19,000. I know a lot of you hear IBM and think expensive, but this is the list price of that server right there that was able to run that mixed graph transactional workload, 700 transactions per second. We're not $1 million solution here, so that's really super positive for you. So this is test cases of accelerating Neo4j graph algorithms with an FPGA. Our CAPI card. And you can see the speed up rates there, anywhere from 134x down to 10. So if you use an accelerator, either a GPU or an FPGA, we're not going to expect 2x better performance. We're looking at 5 or more x. That's the reason you would want to use an accelerator. Just the flip side of this to note, if the algorithms that you have today run fine in the time you like today, you don't have a performance issue or response time issue, you probably don't need this. But what we see more in the AI space and the graph space is the complexity of algorithms. Back to my earlier point, people want to go faster and faster, and they want to move towards real time. So this FPGA speed up of anywhere from 10 to 100 plus x for algorithms becomes more and more interesting. Another key point on this chart is it's not just GPUs, it's also FPGAs that you can bring to bear on this, and we run both on our platform. We do have two cloud offerings. We have a Docker container-based offering called IBM Cloud Private. It also has Kubernetes, so you can pre-package any of these products, including Neo4j, as a Docker container and make them available to your development teams that want to spin these Docker containers up super quickly. and do some DevOps in there, and you could toss Cloud Foundry in there. It is a prepackaged solution, so we can get you that. And then we also have another interesting partnership. This one's based on OpenStack and uses Docker containers. We do have a second partnership with a company called Nutanix, so if you're interested in that cloud platform, I think they have around 9,000 customers. We also have an offering in that space. So one final point I'd like to make before I get off the stage and get the real star of the show on here is that the relationship between data and AI. So if you're going to do machine learning and you're going to do deep learning, you're going to look at algorithm selection. You're going to select a set of algorithms that either do ML or deep learning. And the bridge between ML and deep learning is the end game is speed and accuracy. So machine learning and deep learning algorithms need data, but they need data in a different format than is stored in an SQL or a NoSQL database. So an interesting thing or a use case for Neo4j is when we talk about AI algorithms, we talk about what they really need is the features. Oftentimes they look at work in a matrix or vector type approach. They don't need the raw data, they need the features. So one example is instead of a picture of me, they need the distance between my two eyes or something like that. They just need a feature, they don't need the raw data. It's interesting to look at using Neo4j for feature extraction. So I think this is a really interesting bridge that's going to be super popular going forward in the future. So I would like to now turn it over to my colleague Kiram. Just interesting case study. His group used Neo4j to design the next generation of IBM processors and chips. So I'll turn it over to him and I'll move your slides whenever you want me to. So if you want to go there, and then I'll go here, and then you just kind of give me that move the slide signal.
All right, great. How are we doing on the mic? Excellent. So thanks very much, Chuck. So I just thought I'd spend a few minutes talking about our experience in IBM using Neo4j to design advanced microprocessors. So I think I'm an outlier at this conference. I don't do social networks. I don't do financial fraud. I don't do disease propagation. But fear not. What we deal with are billions and billions of objects. The objects that are related to each other are transistors and circuits. Here's the scope of the problem that we have to solve on the team I work on. We have to design a system consisting of 5 billion components, all of which need to be printed on a piece of silicon that's about the size of a postage stamp, and whose performance needs to be characterized down to the trillionth of a second. That's about the amount of time it takes light to travel a fraction of a millimeter. So we're dealing with billions of things, billionths of a meter, in trillionths of a second. This is a huge big data and analytics problem. And so, a little bit of context for this work. In the field I work in, which is known as electronic design automation, just think CAD tooling for chip design. That's all you need to know. Graphs are nothing new. We've been working with graphs in the EDA field for decades. In fact, I'm willing to bet a dinner, I'll go as high as a dinner, that if you crack open your favorite commercial EDA timing, power, noise, routing, placement, circuit characterization tool. You know what you're going to find underneath the covers if you pop open the hood? You're going to find an in-memory specialized graph database, okay? This is known technology for many, many decades. Why are graphs so popular in the field of circuit? What do circuits have to do with graphs? Well, I think these are reasons that are well known by this audience. Number one is that a graph representation gives us a super efficient means to traverse extremely complicated networks. And that's obviously very important to us. But number two is, as Chuck alluded to, there are a whole family of graph-based algorithms which allow us to take what would otherwise be exponential complexity problems, think path enumeration, and tackle those in a linear time approach. In fact, in the really specialized field I work in, which is timing analysis, it's a well-known fact that we can characterize the circuit performance, the timing characteristics of any path that goes through any circuit in the design with a single number. That, my friends, is how we can tackle 5 billion transistors, analyze the performance thereof in any kind of reasonable turnaround time. Okay, next chart, please. So what's new here? How does Neo4j fit into this picture? Well, historically, there have really been two challenges for the EDA industry. Challenge number one is the distributed nature of our methodology. So it actually turns out that our problems are so complex that we have to take a divide and conquer approach. So in order to design and analyze a complicated microprocessor with 5 billion transistors, we don't have a single graph running on a single machine. We divide the problem into hundreds of partitions. So we have hundreds of semi-related graphs all being run on different machines within our HPC cluster. So the challenge then is, how do we integrate all of this data in a cohesive fashion so that we can feed actionable insights to our design teams? Let's go to the next chart, please. Challenge number two is persistence. Our applications typically stay live for a matter of hours, or maybe in the longest, a period of a few days. Why is that? It's because the design team that we're working with tends to iterate in time frames of days. So once the transistors change, once those 5 billion transistors change, we have to spin up a new version of our application. Well, what does that mean? We can't possibly hold in memory every version of every design that we've ever worked on in IBM. That's not practical. We don't have that kind of memory. So that means that we have to persist results over time. And the way in which most EDA flows tend to persist results is by taking these beautiful in-core, in-memory graph models and serializing those to disk as, guess what? Tables and very, very long, complex reports. Okay? So now we've got hundreds of graphs which are serialized to disk as tables and flat reports. So what does that mean? What that means is that our end users, our designers in IBM, have to make up the difference. All of the beautiful properties of graphs, linear time complexity, super fast traversal, are suddenly lost at the key juncture where we actually have to write a result out to disk for the design team to take action on. What does that mean? How do end users make up the difference? Well, they do so with blood, sweat, and Python and Perl scripts that are extremely complicated and painful to maintain. Let's move to the next chart. So what do we really want? At the start of this year, we came up with really a transformative vision for circuit design. We realized what we really want is we want a persistent, unified graph model which spans the entire hierarchy, so that we can integrate results from every portion of our microprocessor design in one place. We can access those results in real time, and we can package all of the data in consumable web-based services. So this is the role that Neo4j is playing for us in IBM, getting back to Chuck's recursive story. Let me just take you through at a bit of a high level some of the key results that we've been able to achieve. So step number one in our transformation is we've got to get results out of memory onto disk so we can get those into a database. And the way that we do so is we leverage Neo4j import, the very efficient batch importer, which means we have to provide the import script CSV data. So we've written some extremely fast and efficient, using multi-threading, methods of serializing our graph data in a CSV format. So we have a very well-defined schema. Every circuit has a certain predefined set of properties that we want to capture. We export that schema in a CSV format, and really all this chart is telling you is that at the end of the day, the cost to export a full graph out of one of our key EDA tools, which is responsible for timing analysis, is a couple of % on the overall end-to-end runtime. So this is very, very much affordable given the benefit that we get from a graph database. Let's hit the next chart, please. Okay, so once we have data in CSV format, I think we all understand what has to happen next. We've got to ingest the data into our graph database. So we use Neo4j import to ingest data. We use Cypher to index the database. We have a standard template-based Cypher script to index the database. Here's the bottom line, folks. So for our largest full chip graphs, which span the complete hierarchy and occupy order of magnitude 100 million nodes, we're able to import data and fully index the database in under an hour. That is very, very fast compared to the amount of processing time that goes into actually computing these results we want to hold on to. And actually, just kind of one quick editorial note, it turns out to be extremely fast to import data. It's the indexing of the database that's a little bit expensive in this process. So if we could ask one thing of the Neo4j team, it would be any improvements in indexing time would be highly appreciated. Okay, so next chart. I'm just going to share with you a couple of examples to give you a sense of the power of using Neo4j in my space. So this first example is just illustrating our prior way of doing things. And the objective in this exercise is really to do some critical path analysis. We want to be able to solve the longest path problem for a particular circuit in our design. Give me the longest timing path through a particular circuit, which may happen to go through multiple stages of pipelining and latching. This sounds like a simple thing to do if you have a graph, and it actually is simple with our in-core memory model. The problem is that if all the artifacts you have are text-based reports and tables, this turns into a giant SQL join operation, and it's extremely complicated. It turns out that our design team was having to parse many, many gigabytes of tabular data, write extremely complicated Python and Perl scripts to effectively perform a table join, and then somehow in Python and Perl try to solve the longest path problem, which is inherently a graph-based problem, right? So this was very painful for us. Now in the new flow using Neo4j, now that we've got all of the data imported into a live graph database, everything I described in the prior chart can be accomplished with one line of Cypher code, and it executes in 1 second. I mean, that, folks, is how you transform an industry. You go from an impossible to ask question because you don't have the data in the right format to a question you can answer in one line of code in 1 second. That's transformation. You'll see here in the green, we've actually implemented some of our own custom APOC scripts, if you will, which we found is very useful because we have some custom ways of traversing the data. And so we very much appreciate all of the Java APIs that Neo4j has provided us so we can have fine-grained control over how we iterate through the database. Just a quick second example. I'm going to keep this high level again so we don't get into the details of any particular design. This second example, what we're interested in doing is just a transitive fan-out tracing. So it's often the case that folks on our design team have a particular piece of circuitry that they're working on, and they need to know what are all of the storage elements or latches that this particular circuit feeds. Again, this is a really simple problem if you have data in the right format. If you have data in a graph, this is just a transitive fan-out trace. Again, really difficult for our design team to do if all they have to work with are reports and tables. This required uncompressing and parsing many gigabytes of unstructured reports from our EDA tools, having to stitch together the results, having to build in some kind of a graph representation using Python or Perl, which is very painful. This was many, many pages of Python and Perl code that was extremely painful for many design team members to maintain and really hindered our productivity in IBM. So if you move to the next page, in the new flow, we can accomplish everything I've described in essentially one line of code, it's a common theme, which executes in under 1 second. So the Cypher here gets a little bit complicated, but if you stare at it, you can see what we're doing is we're identifying a particular circuit in the design by name. Once we find that circuit, we call an APOC procedure to perform custom path tracing. Again, leveraging all of the power of the Java APIs that Neo4j has exposed to us. and then we can return data and format it in any manner that we want. Here we're just showing a little, go back to the previous page please. We're just showing a little graph representation which shows that the pattern match is somewhat non-trivial. Each of the fan-out elements that we're trying to search is actually a triad of nodes. And so we write a custom APOC routine that allows us to perform a very specialized type of fan-out tracing, which is looking for a particular pattern in the graph that's relevant to our design teams. Okay, last page, please. So I just wanted to keep this nice and tight, give you a couple of examples of how we've used Neo4j to really help boost the design team. Just kind of playing right along with Chuck's recursive story. And I can tell you firsthand that we're getting a lot of power in IBM, pardon the pun, out of the combination of IBM Power Systems. The entire system that I described is running on Power 8 systems. At Neo4j, that combination has really proved to be transformative for us, and really appreciate all of the solid co-development and support that we've got. Thanks very much. Any questions?
I'm going to just wrap it up here, and then we have 9 minutes or so left to take a couple questions. But we are at the IBM booth, so if we don't get to your questions, you have my email here, and then we'll be over at the IBM booth afterwards. So a couple lessons learned in this journey. So incremental value from hardware comes from price, performance, and scaling, in particular for large graphs initially. And now the newest thing is acceleration technology and the combination of graph and AI benefiting both from FPGAs and GPUs. So like I said at the beginning of the presentation, there is something new happening in hardware. It's really two stages, fast memory and larger, faster memory. And that accommodates the growth in Neo4j graphs and different types of memory being available to you at much lower price performance points than way in the past. And then the second thing is specialized accelerators, either GPUs for AI work and or FPGAs from companies like Xilinx and Nalitech to accelerate graph-based workloads, in particular graph-based algorithms. The second thing is we do find all the customer engagements that we embark on with Neo4j benefit from two things greatly. One is access to Neo4j experts to get your first 5 to 10 graphs created in your environment, with your use cases, with your data. It doesn't really matter if your next door neighbor can create graphs really quickly. We need to work with you to get the Neo4j experts available to you to create the use cases that are identified to you with your data as being high value, and then get those graphs created and get you able to do that on your own to fast track that. We find between 5 and 10 is kind of a number that comes up a lot after you've created your first 5 and 10 graphs with your use cases, with your data. Then you're much more comfortable and you know what you're doing and you can do that. The second thing is to reduce your risk, your cost, and really accelerate your time to value proof of concepts. So we do have, for qualified customers, a free proof of concept available. We've had a number of those occur in our database environment, including with Neo4j, where you can dial in remotely to our system, which has Neo4j on it, on Power, load your data. We're not going to look at your data unless you want us to. You can anonymize it. You can give it to us or not give it to us, or however you want to do it. You don't have to come to our place. You can dial into it. We'll give you the secure access and that kind of stuff. And then you run a proof of concept with our experts and Neo4j's experts on your workload, dialed into our stuff, quick POC, beneficial for 3 areas. One is you learn what works, you build your skills, and then because it's a proof of concept, you learn about what didn't work and any false assumptions you may have had or we may have had. So really beneficial for those 3 things, not just one thing. We do have cloud offerings. We do realize that many of our clients now, especially in the database analytics environment, are asking for cloud solutions. I'll give one quick example. If I go back a year ago, we really had nothing on our drawing board around cloud. Now we have like 4 different cloud solutions in the space I work in. So we're seeing a large increase in interest around running both database and analytics on cloud, including graph on cloud. So we do have multiple solutions to help you increase the velocity adoption of Neo4j. And second thing I like about cloud is the new business models it opens up. It's not only velocity of adoption, I think it is the new business, the creative thinking around that. And then the final thing is a lot of this optimization is because both our engineering teams worldwide work together, everywhere from designing our hardware with Neo4j to changing Neo4j based on some customer workloads running on our hardware. So we have 5 minutes left. I can take any questions if there are any. If you don't feel comfortable asking questions but want to get back in touch with me, let me put this up so you just see it one more time. In case you want to have a more private conversation, that's cool with me. And there's my contact information. So are there any questions you'd like to ask now? If not, we're at the IBM booth, and then here's my email here.
FPGAs you use?
Yeah, so the question is, can we elaborate on the FPGA? So we use FPGAs from Xilinx, and the card is from Nalitech. And those FPGAs are programmed in a language that we recently came out with called Cappy Snap, which is C, C++, and or Go-like. And you would basically code up an interface to that to accelerate an algorithm. That's sort of case one. The second case is you can also use the accelerator, the Cappy card accelerator, actually has some memory on it. So just as an example, if you don't have a CPU problem, but you have a memory fetching problem, that FPGA, even though it's really small, it's like that big, has or can have 4, 8, or 16 mega or even larger amounts of memory on some other variants of that. You can actually prefetch and put some data from Neo4j, the next X amount of bytes, into the memory of the FPGA. So some algorithms just start searching through a linear array of data. You can actually leverage the FPGA for beyond programmable gate array acceleration to actually using the memory itself. The other thing I'd like to mention about an FPGA that does have a slight advantage over a GPU is we can change the architecture and organization of an FPGA in 60 seconds. So if you can imagine structuring optimized gate array for one algorithm, making your own computer that's just really super fast for one algorithm, and then that algorithm slightly changes, in 60 seconds we can rechange the architecture and organization of that programmable gate array to run the new algorithm that you just tweaked. So it doesn't take weeks, hours, days, anything like that. 60 seconds we can change it and reflash it, and we're ready to roll with your newer algorithm to accelerate that. Yeah, so in Power8 systems, you have two type of adapter slots. You have PCIe slots, and you have NVIDIA NVLink technology slots. So in the PCIe slots, PCIe 3 with Power8 or PCIe 4, twice as fast with Power9. You can put things that plug into PCIe slots, accelerators, or older style NVIDIA cards like a K80 card, 256 cores. And in our Power8 and Power9 processors, we also have slots that you can put the latest NVIDIA GPUs in, the Tesla or the P100s, either one. And then we have faster links between our CPU and GPU for NVIDIA GPUs, which is called NVLink technology. In the future, about a year from now, that Cappy protocol I talked about will be a single transport protocol that will handle traffic from an FPGA and a GPU over a Cappy interface, which goes at 25 gig per second instead of just 16, which is what you get with PCIe 4. So impressive interconnect technology combined with the options to put both FPGA cards and GPU cards. You can also put a Mellanox switch in some of our servers. So if you want to get to NVMe, very large arrays of disk over fabric, 40 gig, 100 gig kind of thing, you can get those switches from Mellanox. Often useful in a cloud environment as well. It's just super fast access to fast fabric. So a lot of interconnect options. And that comes about because of our partnership with over 300 different companies in designing our system. So I have one chart I present. If you open up the diagram of a power system, it's like we get componentry from the best providers from all over the world. Our HDD, our SDDs from Samsung, our different providers of all our stuff, and then we're just leveraging that innovation going forward and adding more and more members. Just quick thing, I don't know if you know that Google is a open power partner, Rackspace, many companies. HP, Dell, you wouldn't think that, but they're, we have a lot of different types of partnership in the hardware industry. And like I said on this, the biggest thing happening in hardware beyond the standard CPU, memory, and I/O kind of stuff is the accelerator technology, not just GPUs, but also FPGAs. So I think these guys are going to cut me off in 10 to 20 seconds. So is there one other super quick question? Okay, thanks everybody for coming. Thank you.